Welcome. My name is Freystein Sigmundsson, and in this module I want to tell you about interpretation of observed crustal deformation fields, in particular how we can model the process of magma transfer at depth, thereby inferring depth of magma storage and volumes of magma moving. When interpreting volcano deformation, a common assumption is that the Earth behaves like a spring, responds instantaneously to forces, and that the surface of the Earth is flat. This is the so-called elastic half-space assumption, and it leads to simple analytical equations describing ground deformation that are widely used, even though deviations from these assumptions may be significantly influencing the outcome. So, the model most frequently used to interpret the deformation assumes that there is a point source of pressure or a small source of pressure within an elastic half-space, as shown in this figure. It applies both to surface deformation due to magma accumulation prior to an eruption, when pressure change is positive, or magma withdrawal from a magma body during the eruption when pressure change is negative. The model is commonly referred to as the Mogi model, named after the Japanese volcanologist Mogi, who applied this model to deformation, observed by repeated leveling in relation to an eruption in Japan that occurred in 1914. Now, the accumulation of magma inside the crust is modeled as a source of increased pressure, written as delta P, within a spherical source volume in an elastic half-space. A point source of pressure refers to the assumption that the radius of the source, denoted as A in this figure or alpha, is small compared to its depth d. The depth is measured from the surface to the centroid depth of the spherical body. Later work has shown that this approximation is valid as long as the ratio over d over alpha to d to the fifth power is small. So actually, it is quite a good approximation. Under these assumptions, the mathematical equations describing the behavior of an elastic material are solved by applying a pressure change at the boundary of the spherical source. No forces are applied on the surface of the half-space, so it is free to deform in response to the subsurface processes. 4 parameters are needed to fully describe the model behavior. There are 3 parameters for the location of the source, latitude, longitude, and the depth. And the 4th parameter is the source strength. It depends on both the properties of the source as well as the surrounding host rock, that is, the properties of the elastic half-space. And this model results in relatively simple surface deformation field that is radially symmetric. It is thus convenient to express the deformation in a coordinate system with a center in the same horizontal location as the surface projection of the source. We can then use a coordinate system where the horizontal distance from the source is on a horizontal axis that we refer to as r. The model predicts both horizontal displacement in the radial direction, directly from the surface projection of the source center, and vertical displacement as shown with the equations and graphs in this figure. We use the letter U to denote displacement, vertical displacement, or the height change that can be referred to as U subscript Z, with Z referring to the vertical direction. The horizontal displacement is U subscript R. The displacements that depend on the horizontal distance from the source and the depth of the source, as the equation shows, as well as the source strength parameter indicated with the symbol C. There are 4 independent parameters that decide the predicted displacement: latitude and longitude of the source, that decide the distance from the source, and then the depth and the source strength. But what influences the source strength? The source strength parameter depends on the properties of the source and the half space as shown in this figure and equations. Equation 1 in the figure shows how the source strength scales with the source properties, the applied pressure change times the radius of the source to the third power, as well as properties of the elastic material, its shear modulus, denoted with the Greek letter mu, and its Poisson's ratio, denoted with the Greek letter nu. In general, it is not possible to separate the contribution of each of these parameters separately. Any combination of these parameters that result in the same value for the source strength parameter will produce the same surface deformation. For example, the radius of the source nor the pressure change can be inferred separately from ground deformation, only its combination as shown in equation 1. Equation 2 is an alternate expression, equally valid, that shows the source strength can also be written in terms of the volume change of the spherical source, denoted by delta V. This is a somewhat simpler representation, as it only depends on the volume change of the source and the Poisson's ratio. Seismic studies, they indicate the Poisson's ratio for the Earth is about 0.25, so this equation allows one to infer the volume change of spherical source from surface deformation measurements. Equation number 3 is another equally valid expression. It shows that the source strength equals the product of maximum surface displacement directly above the source, denoted by h subscript 0 times the depth to the source squared. This equation can be used to infer the source strength parameter from surface deformation field that can then later be used, for example, together with equation 2 to infer the subsurface volume change. And the predictions of the Mogi model when compared to measured surface deformation on a volcano thus provides a relatively simple manner to estimate the horizontal location and depth of a magma body causing the deformation, as well as its volume change, as long as the assumptions of the model are appropriate. Let's have a look at some of the examples of the use of the Mogi model, and this picture was also on the initial slide. The pioneering work of Mogi was a study of the 1914 eruption of the Sakurajima volcano in Japan. The volcano shown in this figure is on the border of the mostly submarine Era caldera at the southern Kyushu in Japan. The lower photo shows a view from the base of the Sakurajima volcano across the Kagoshima Bay towards the city of Kagoshima. The Sakurajima volcano is very interesting. It has had very frequent explosive activity for decades, but 1914 was its most recent large explosive and diffusive eruption with a volcanic explosive index way equal to 4. In 1958, Mogi published a paper entitled Relations between the eruptions of various volcanoes and the deformation of ground surfaces around them. Here is what he did. Mogi had access to leveling data collected before and after the 1940 eruption along leveling profiles shown in the map on this figure. The leveling measurements were carried out mostly along the coast of the bay where the Era caldera is. The measurements, even if spatially very limited, indicated a concentric subsidence pattern with a center out in the Kagoshima Bay. Mogi, he plotted the inferred vertical displacement at the leveling sites as a function of a distance from a central point close to the center of the caldera. The result is shown in this graph here. There is a very clear systematic pattern. The black line is a prediction for a model of point source of pressure within an elastic half space. And the depth of the best fitting source in this model is 10 km and the maximum subsidence is over 1.5 meters. The fit is good. The model parameters were found by trial and error. the longitude and latitude of the source used to calculate the radial distance of the sides, shown on the x-axis, and the other two parameters are the depth and the vertical change above the center of the source. Let's next have a look at the data from Krafla caldera in North Iceland from the Krafla rifting episode from 1975 to 1984, when we had the period of diking. Leveling and tilt data as well as seismicity from this episode were revisited and studied by Elias Rafn Heimisson and colleagues. Panel A in this figure shows vertical displacement inferred from leveling, and each colored dot shows observed vertical displacement in the time period following the first large deflation event in December 1975 until 26 April 1977, with color giving the amount of displacement according to the scale shown. The Krafla caldera faults are shown by solid black lines. And in this time period, stations within the Krafla caldera experienced cumulative uplift of more than a meter and displacements rapidly decaying with distance from the center of the caldera. Panel B shows predicted vertical displacements using a Mogi model. The parameters of a Mogi model, longitude, latitude, depth and strength, are adjusted to provide a best fit to the observations. We see that the resemblance between panels A and B is very good, meaning that the model fit is good. This is witnessed in panel C, which shows the difference between the observed and predicted values that we refer to as residuals. The residuals are mostly in the range of plus minus few centimeters or few % of the observed values, confirming that the fit is good. Therefore, we can say that a Mogi model fits this dataset well. This process exemplifies the general approach of volcano geodesy to derive models. We have a geodetic dataset, as shown in panel A. We make predictions of expected deformation pattern from a model, and we adjust the model parameters so the predictions of the models, shown in panel B, best fit the observations. We evaluate the residuals, the difference between observations and models, shown in panel C. The best fitting model parameters are chosen such that they minimize the residuals. During the Krafla rifting episode, a series of leveling surveys were carried out, and there was furthermore a water tube tiltmeter operating as well as electronic tiltmeters. These observations allowed to infer the temporal evolution of a Mogi source that was located close to the center of the Krafla caldera, and the results are shown in this graph. For each time, a separate independent set of best-fitting model parameters was found. The blue curve shows the inferred volume change of a Mogi source throughout the rifting episode, and in red the inferred depth range according to modeling. The volume change shown is in units of cubic kilometers. At the end of the rifting episode, this modeling suggests that the cumulative volume increase of the source had occurred despite all the deflation events, and that it was on the order of 0.3 cubic kilometers. The inferred depth of the Mogi source is somewhere in the range 3.3 to 4.6 kilometers. These bounds are what come out of the modeling. It may be possible that in reality the location was always the same, and the scattering depth values represent the uncertainty. If one would fix the depth to be constant for the whole period and then find the best fitting parameters, this would influence the values of the other model parameters, because there is in general trade-off between model parameters when we fit observations like this. The graph shows that when the main jumps occur in the best fitting depth, there is also a jump in the inferred volume change. Some of these jumps would go away if the depth would be held fixed when deriving the other model parameters. Let's next go to the Eyjafjallajökull volcano and look at a study by Erik Sturkel and colleagues. The background figure here shows topography, and the black outline marks the extent of the Eyjafjallajökull glacier that covers the top part of the volcano. This figure shows mostly predicted deformation, that is a predicted pattern of horizontal displacements for a Mogi model. The black are model predictions for a Mogi model located directly under the point where all the black arrows point away from. The source is at 3.5 km depth with a maximum uplift of 35 centimeters directly above it. The Mogi model is symmetric, so horizontal model displacement will always point directly away from the source. Also shown in the figure are few white arrows at GPS sites, shown as white hexagons available for the time period from July 2008 to July 2010, when an intrusion occurred. The few stations available show displacements similar as the model predicts. Of course, it would have been beneficial to have a larger number of observation stations. Further studies and more data have suggested that a SIL model actually fits better these and other observations at Eyjafjallajökull. Here are results from another volcano in South Iceland, the Hekla volcano. The main map in this figure shows local horizontal velocity arrows for the time period from mid-2000 until 2010. Observations are in black and white are model predictions, according to a study by Halldór Geirsson and colleagues. The most recent eruption at this volcano was in 2000 prior to these observations. Following that, the GPS velocities appeared to have been relatively steady. The background map shows shaded topography and Hekla volcano is approximately in the center of the deformation pattern. The white triangle there shows the inferred center of inflation at Hekla. There is also another local deformation source in this model that has, however, only a minor contribution. This is a deflation source at the location of the inverted white triangle east of Hekla at the so-called Torfajökull volcano. Notice the scale at the lower left for the displacement arrows, 5 mm per year. Accordingly, the velocities here are small. The observed velocities, as shown here, are importantly corrected for the effects of plate spreading and glacial isostatic adjustment in Iceland due to present-day glacial retreat. Otherwise, it would not have been possible to see the contribution of deformation related to processes at Hekla. This type of correction for other sources of deformation is typically needed in volcano geodesy, and it introduces some uncertainty on the exact ground deformation due to magmatic sources. The panels on the left in this figure show vertical and radial velocities in millimeters per year as a function of distance from Hekla. We see even if there is a large scattering in data and the signal-to-noise ratio is small at each side, then there is a systematic pattern. The black solid line is a prediction of a best-fitting Mogi model that has a source depth in the range of 22 to 29 km and increase in source volume in the range of 17 to 30 million cubic meters per year. The dashed line shows predictions for another geometry of the deformation source, assuming the magma source is in the form of a vertically aligned pipe. We see that this model can fit about equally well. The best fit pipe model has a top depth in the range of 9 to 13 km and bottom depth in the range of 17 to 28 km. It has a lower volume change than the spherical model, or about 8 million cubic meters per year. In any case, the model confirms that the inferred pressure increase at Hekla volcano is of deep origin and there is steady increase of pressure under the volcano with time. The examples we have covered here demonstrate how the Mogi model can successfully be used to constrain shallow and deep deformation sources. However, in all cases, it is important to keep in mind that the inferred model parameters are dependent on the fundamental assumptions of the model, namely uniform elastic material properties around the source and spherical geometry for the magma body involved. So, if you want to study further, I recommend what you do is go to the paper of Mogi, read it, see how this initial study was done of volcano deformation and how Mogi inferred the changes occurred in the subsurface, and then go and find a recent paper on an eruption of your choice and see how geodetic models have been used to study that eruption and compare them. And that would be a very good way to expand your knowledge. Thank you.